Chapter 13, Fluids. Fluids cover, fluids at rest, Pascal principle, Archimedes's principle, the equation of continuity, Bernoulli's equation. You can find them in a timeline. Fluids at rest. Fluids and the world around us. Fluids, which includes both liquids and gases, play a central role in our daily lives. We breathe and drink them, and rather vital fluid circulates in the human's cardiovascular system. There's the fluid's ocean and the fluid's atmosphere. What is a fluid? A fluid, in contrast to a solid, is a substance that can flow. Fluids can form the boundaries of any container in which we put them. They do so because the fluid cannot sustain a force that is tangential to its surface. In a more formal language, a fluid is a substance that flows because it cannot withstand a shearing stress. It can, however, exert a force in a direction perpendicular to its surface. In fluids, there's no orderly long-range arrangement of constituent atoms. Density and pressure. With fluids, we are more interested in properties that vary from point to point in an extended substance than with properties of specific lumps of that substances. It is more useful to speak of density and the pressure than of mass and force. Density, rho, equals delta m over delta v. The unit is kilogram cube a meter. In theory, the density at any point in fluid is the limit of this ratio, as the volume element delta V at that point is made smaller and smaller. In practice, we assume that a fluid sample is large compared to atomic dimensions and thus smooth with uniform density rather than lumpy with atoms. These assumptions allows us to write above equation the form rho equals m over v, not delta m delta v, where m and v are the mass and the volume of the sample. Note that the density of a gas varies considerably with pressure, but the density of a liquid does not. That is, gases are readily compressible, but the liquids are not.
Air is compressible. If we fill the syringe with air and place it between two wooden blocks, a weight placed on the upper block can easily compress the air. Water is not as compressible. If the syringe is filled with water instead of air, and the demonstration is repeated, even large amounts of weight do not compress the water significantly.
Pressure. P equals delta F over delta A. The unit is Pascal. 1 Pascal equals 1 Newton over square meter. We have a sensor for this one. We can apply the area as delta A, the force delta F, and we get the pressure. In theory, the pressure at any point in the fluid is the limit of this ratio, as the area dA of the piston center on that point is made smaller and smaller. However, if the force is uniform over a flat area A, we can write P delta F over delta A as P equals F over A. When we say a force is uniform over an area, we mean that the certain force would be measured at every point of the area. We found by experiment that at a given point in a fluid at rest, the pressure P defined by P equals F over A has the same value no matter how the pressure sensor is oriented. So the pressure is a scalar having no directionality properties. The Pascal is related to some other common non-metric system pressure units as follows. 1 atmosphere equal to 1.1 times 10 to the 5th Pascal is around 760 torr. The atmosphere is, the name suggests, the approximate average pressure of the atmosphere at sea level. This one, atmosphere. The torr, named by Torricelli, who invented the mercury barometer in 1674, was formerly called the millimeter of mercury. Millimeter of mercury.
We'll use this water manometer driven by a flexible rubber diaphragm to show that pressure in a fluid is independent of direction. When the diaphragm is lowered into a jar of water, the manometer indicates the pressure increase with depth. When the diaphragm is held at a constant depth and turned to different directions, the reading on the manometer stays constant. The pressure in the water is the same in all directions.
This is some pressure where it goes through. The best laboratory vacuum is 10 to the minus 12. That's very low, very low. That's a vacuum, okay? The center of sound, you have a pressure 10 to the 16. Huge pressure.
We'll use these two small hemispheres to demonstrate the force due to air pressure. If the hemispheres are placed together with air inside, pressure is the same inside and outside, and the hemispheres are easily separated. But if we remove the air from the inside with a vacuum pump, the air pressure on the outside is no longer balanced by pressure on the inside. The hemispheres will support a large weight without separating. When air is allowed back in, the hemispheres fall apart. This animation shows the forces due to air molecules striking the inner and outer surfaces. Normally they balance, but when the air is removed, the force on the inner walls vanishes. The unbalanced force on the outer walls must be overcome to separate the hemispheres.
These thick glass plates have surfaces that are microscopically flat. When they are pushed together, the air between the two faces is squeezed out. The atmospheric pressure outside the plates now holds them together. use the power of atmospheric pressure to launch a rubber ball at high speed. The rubber ball is put inside this long tube, and both ends of the tube are sealed with metal plates. A vacuum pump attached to the tube then removes the air from the tube. When the tube is completely evacuated, the metal plate nearest the rubber ball is knocked off. The rush of air into the tube blows the rubber ball out the other end of the tube at high speed. This thin rubber sheet will be used to demonstrate the large forces produced by air pressure. When the sheet is placed on top of this stool, the air between the sheet and the stool is driven out. The air pressure on the top of the sheet holds the sheet to the stool with enough force to allow the stool to be lifted off the ground with the sheet.
Fluid at rest. We look at this cuboid, okay, with its cross areas A, okay, this is length, okay. Okay, look at one surface at the level Y1. This one is level Y2. This pressure we call it P1. This level pressure is P2, okay. And then we look at this, what is physics? First, this cuboid is at rest. That means the total sigma force equal to 0, right? Yeah. Then second, how many forces vertically they have? The first one is the gravitational force mg. Another one is the force from the fluid on top floor, those the F1, and the F1 is going down. Another pressure is from liquid, it's called F2. Okay, so we have, it is at rest, it is at equilibrium, the sigma F equal to 0 vertically. So we have F2 equal to F1 plus mg. What is F2? F2 is equal to the pressure times the area. F1 is pressure times area, right? Yeah. These two pressure are different because the different depths, okay? And then M, this mass of this cuboid is equal to rho times V. Rho is the density of water. The V is equal to area multiplied by the height. The height is Y1 over Y2, okay? Because we take the y's upward as a positive direction. So in this case, y1 is larger than y2. So this is a positive number, okay? And we put all these black, this white, and the blue inside. We get F2 and P2A equal to F1 P1A equal to mg. M is rho A y1 minus 2g. So this equation we cancel out A. Okay, we get P2 equal to P1 plus rho g y1 minus y2. Let me a little bit change this one. Suppose y1, this cuboid is on the top. y1 is 0, okay, and y2 is minus h. So in this one, P1 is the P0. What the P0 is the atmosphere pressure on the surface. Okay? So we put those inside. Okay, we get P at this point, P2, P equal to what? P equal to P0 plus rho GH. This is the fluid at rest. That means the pressure at deep point H, okay, equal to P0 plus rho GH. Pressure at depth h. We see this is references at the surface of the liquid, y equal to 0. And this is a P0 is atmosphere pressure. And this is a point P in the deep H in the water or in the liquid. Okay. We see the pressure P equals P0 plus rho GH. The pressure at the point in the fluid in the static equilibrium depends on the depth of that point, but not on any horizontal dimension of the fluid or its container. Thus, above equation holds no matter what the shape of the container is. In the above equation, the pressure P is said to be the total pressure or absolute pressure. The difference between an absolute pressure and an atmosphere pressure is called the gauge pressure. The name comes from the use of a gauge to measure this difference in pressure.
This is an electronic pressure gauge which has a pressure sensor at the bottom. Blowing into the sensor through a tube increases the pressure and drives a bar graph display whose length is proportional to the pressure at the sensor. When the pressure gauge is placed in a column of water, the display shows that the pressure increases in direct proportion to the depth of the sensor. If we replace the water in the column with alcohol, which has a lower density than water, how will the pressure readings be affected? The reading is lower in alcohol than at the same depth in water, but it is still proportional to the depth.
The mercury in this U-shaped tube is in equilibrium when the surface of the mercury is at the same height in both sides of the tube. But when colored water is added to one side, the fluids come to equilibrium with their surfaces at different heights. The pressure at the bottom of each leg must still be the same, but the amount of fluid required to produce that pressure is different on each side.
Sample. A novice scuba diver practicing in a swimming pool takes enough air from his tank to full expand his lungs before abandoning the tank at the depth air and swimming to the surface. He ignores his instructions and fails to exhale during his ascent. When he reaches the surface, the pressure difference between the external pressure on him and the air in his lungs is 70 torr. From what depth did he start? What potentially lethal dangers does he face? We look at this equation, okay, we see the P minus P0 is 70 torr. Delta P is equal to rho GL. And this number is given 70 torr. Okay, so we can find the air. Right? Remember that one. This one should be used to Pascal. And this is the torr. Okay, so we have to 706 torr is 1 atmosphere, 1.11060. So this is 9,300 Pascal. We put this inside, we get air. This rho is the density of water, 998. This is the gravitational acceleration, 9.8. So the depth is 0.95 meter. It's only 1 meter, it's not 5. But this is not deep, yet the pressure difference of 9.3 kilopascal, about 9% of atmospheric pressure, is sufficient to rupture the diver's lungs and force air from them into the depressurized blood, which then carries the air to the heart, killing the diver. If the diver follows instructions and gradually exhales as he ascends, he allows the pressure in his lungs to equalize with the external pressure, and then there's no danger. Example: the U-tube in the figure contains two liquids, in a static equilibrium. Water of the density rho W in the right arm, and oil of unknown density rho X in the left. Measurement gives L equals 135 millimeter and D 12.3 millimeter. What is the density of the oil? Let's look at this one. The physics here is interface. We see on the interface, the left side and the right side, their pressure should be the same. This is the physics. So let us see what is the interface pressure. Let's see, on the right side, this is water equal to rho GL, P0 per rho GL. And here is P0 plus rho X G air plus D. So from this equation, we cancel out the P0, we get a rho X. We put a number inside, and we get this about 915 kilogram per cubic meter. This equation, nothing to do with G and nothing to do with P0. Measuring closure. The mercury barometer, this is mercury, this is vacuum, P equals 0. This is air, the pressure is air pressure, atmosphere. Whatever the shape it is, we see this is the same, H, K, this is the same. It's nothing to do the shape or the horizontal situation. Now we see P2, P2 equals P1, plus Y1. What is 1? And this is a 1, this is a 2, So the pressure here equal to P1 plus rho G, Y1 minus Y2, This is Y1, we take it as 0, reference here, And we see Y2 is H, Y2 is H. And we see P1 is P0, the atmosphere, and P2 is 0 because it's vacuum. We put this one inside this equation, we get P0 equal to rho GH. So from this H, from the density of this mercury, we can measure the P0, that means the atmosphere. This is called millimeter mercury, or torr. The column height in millimeters is numerically equal to the pressure in torr, only if the barometer is a place where G has an accepted standard value of 9.80665 meter per square second, and the temperature of the mercury is 0 degree. Only in this situation, this is equal to this one. The open tube manometer. This is the open. This is the pressure we're going to measure. We will see this one. This is H, and we find P2 here equal to P1 times Y1 minus Y2. Right? This is H. With Y1 we call it 0. Y2 is minus H. So this is H. We get it. P1 is here, is equal to this open tube. So this is equal to atmosphere pressure. And then P2 is the pressure here, is the pressure we're going to measure. So this is the gauge pressure. PG at this point is P2. Is P2 is P minus P0. This is the pressure P. This is P0 time. And this one, rho GH, remind this one, we call the gauge pressure, not absolute pressure. Okay, it's minus atmosphere pressure. An open tube manometer measures the gauge pressure Pg of a gas, which is its real pressure minus the atmosphere pressure. Pascal's principle. Pascal's principle. We have a liquid, okay, and we know at point P in the depths of H, it has P plus external pressure plus rho GH. This is on the surface. If we put something on top of it, okay, then we'll have to see the change. The change will go this one, okay. The change of pressure, the change of the surface pressure, and with this one. And we found that this is 0 because H never changed. In other words, the change of pressure at this point equal to change of pressure at this point. This is called Pascal principle. Pascal principle. A change in pressure applied to an enclosed incompressible fluid is transmitted undiminished to every portion of the fluid and to the wall of the container. This is okay. Pascal's principle at a hydraulic lever. We see this kind of we call it is a lever, hydraulic lever. The characteristic of this one, this is very small AI, this is very large A output. We put a force F1 pressure tape, and this one we go up, you get a FO output. What the relationship, and we see this one, Fi over AI, the pressure AI, this is delta pressure, that equal to this one delta pressure. This is what the FOAO. Now from this we can find FO equal to Fi times AO over AI. If this area is much larger than this one, we can find FO is much larger than this one. So the jack can pump up the car because force can be very large. At the same time, we see the volume of the liquid oil you go up equal to the volume of the liquid go up. Okay, this volume is the depth DI AI, and this value is DO AO. They equal the same thing. So we find what P output is very large and D output is very small, very small. So in other words, the work done is the same. This is the work done by input force. This is the work done by output. That's it. With a hydraulic lever, a given force applied over a given distance can be transformed to a greater force applied over a smaller distance. Work done is the same.
This hydraulic press will be used to show how fluid pressure can multiply a small input force into a large output force. Pressing this lever down with the force of 2 hands is enough to break a piece of wood or bend a thick piece of metal. This animation shows how it works. 2 oil-filled cylinders with different diameters are connected by a tube. Each cylinder is a tightly fitting piston. Pressing down on the lever moves the small piston down, increasing the pressure in the oil. The increased pressure acts on the larger surface area of the second piston, pushing it up with a force that is larger than the downward force on the small piston.
When an object is submerged in water, the water pressure on it increases with depth. We can use that pressure to hold a glass plate onto the bottom of this truncated glass cone, which is filled with air. The air pressure on top of the plate is less than the water pressure on the bottom of the plate. The difference in pressure results in an upward force that holds the glass plate onto the bottom of the cone. If we turn the cone over so that the small end is down, the plate will no longer be held against the cone. What causes the difference? As this graphic shows, the area of the pressure differential is smaller for the small end of the cone. That results in a smaller total upward force on the plate.
Archimedes' principle. Archimedes' principle. When a body is fully or partially submerged in a fluid, a buoyant force Fb from surrounding fluid acts on the body. The force is directly upward and has a magnitude equal to the weight of mfg of the fluid. That's the weight of fluid that has been replaced by the body. The buoyant force involved two things. One is the fluid. This is the weight of the fluid. How much this mass is replaced by the body submerged in the fluid. Okay, so two things. One is the submerged body, one is the fluid. Okay, so there's the force equal to the mass, the weight of the fluid replaced by the body. The force is directed upward and has a magnitude equal to the weight mfg of the fluid that has been displaced by the body.
This demonstration will show how the buoyant force on a submerged object is related to the amount of water displaced by the object. This aluminum cylinder and pail hang from a scale, which shows the total weight to be 29 newtons. We'll lower the cylinder into this water container, which has an overflow spout. When the cylinder is submerged, the reading on the scale decreases to 20 newtons. All water displaced by the cylinder will flow into a beaker. If we pour the water that was displaced by the cylinder into the small bucket hanging from the scale, how will the reading change? The scale now reads the same as before the cylinder was lowered into the water. The buoyant force on the cylinder is equal to the weight of the water displaced.
Floating. When a body floats in a fluid, the magnitude Fb of the buoyant force on the body is equal to the weight mfg of the fluid that has been displaced by the body. This is very crucial Archimedes theory. So all these pressure, you have a result in Fb, buoyant force, upwards. Okay, we look at the magnitude of upward is the weight of the fluid replaced by the body. If the body is heavier than the flow, so this is gravitationally is larger than the buoyant cover, it goes down. If the body's gravitational force is smaller than the buoyant force, it will fall up.
Why do objects seem lighter when they are put underwater? We'll use this pair of kitchen scales in a frame to find out. The upper scale shows the weight of this aluminum cylinder. The lower scale shows the weight of this container of water. If we lower the cylinder into the water, how will those readings change? The weight of the cylinder appears to have decreased by 2 pounds, while the weight of the water appears to have increased by the same amount. The water is pushing up on the aluminum, and the aluminum pushes down on the water by an equal amount.
We'll use these 3 blocks of wood to demonstrate how density affects the depth at which objects float. This block is cut from balsa wood, with a density of about 0.14 grams per cubic centimeter. When placed in water, it floats with only about 1/7 of its volume submerged. This is a block of pine, with a density of about 0.5 grams per cubic centimeter. It floats with about half of its volume submerged. This is a block of ironwood, with a density of about 0.9 grams per cubic centimeter. When placed in water, it floats with about 9/10 of its volume submerged.
This column contains 3 liquids with different densities. In order from the bottom, they are mercury, carbon tetrachloride, and water. We'll drop 3 objects made of different materials into the liquids to see where each object floats. Here is a piece of iron. It sinks through the first 2 layers and floats on the mercury. Here is a piece of bakelite. It sinks through the first column and comes to rest atop the carbon tetrachloride. This piece of wood floats atop the water. In this tank of water, we have a small plastic bottle full of air with an opening at the bottom. A weight at the bottom of the bottle makes the overall density of the bottle slightly less than that of the water. A syringe is connected to the side of the water column. As the syringe is compressed, the increased pressure compresses the air inside the bottle and increases its overall density. When the density of the bottle is greater than the density of the water, the bottle sinks to the bottom of the tank. Reducing the air pressure in the tank expands the air inside the bottle and returns it to the surface. If the pressure is continually adjusted, the bottle can be kept in the center of the water column.
Sample. The tip of the iceberg in popular speech has come to mean a small visible fraction of something that is mostly hidden. For a real iceberg, what is its fraction? We see the whole weight of iceberg is V iceberg, rho ice, so this is the mass, G is weight. The buoyant force is equal to the weight of the water, which was replaced by the iceberg, is called V under. Okay, this is water's density. They should be the same because balance, when they balance, the force downward is equal to force upward. In this case, so with the rho I V I G equal to rho W V under G. And the percentage is VI minus V under divided by VI equal to 1 over V under over VI. And from here, V divided by VI equal to G cancel equal to rho I over rho water. We put this number inside. Okay, this is the density of ice. This is the density of water. Okay, we get about 10%. So when we see the iceberg, we say 10% above the water, 90% is under the water. Sample. In the figure, a block of density rho equals 800 kilogram per cubic meter flows face down in a float of density rho F equals 1200 kilogram per cubic meter. The block has height h 6.0 centimeter. Question 8. By what depth h is the block submerged? Now we need a balance. What a balance? The balance is the buoyant force equal to the gravitational force because it's at rest. Okay, acceleration is 0. And we write that the force, the buoyant force equal to gravitational force. Well, this one equal to the weight of a liquid, which is occupied by the stuff. So it is a V5 floating, is merged part in the float. Okay, and this is the gravtation of the block. So the total V. These V are different. This is part of it. Okay, so in this case, I can find FV. Okay, there's V equal to area multiplied H. Okay, and the total V is area plus big H. Okay, we know both of them. So in this case, we know that's H. Okay, H equal to H rho over rho final. We put a number inside. Okay, we use the centimeter as a unit. We get 4.0 centimeter. The key point is this one. Okay, that's physics. The buoyant force equal to gravitational force. Okay. Question B. If the block is held fully submerged and then released, what is the magnitude of its acceleration? Let's see the force. If it's submerged fully in the liquid, and this force is different from others. This is its weight, okay, and G. Okay, so we see the acceleration equal to FP over FG over M. What is FV? FV is total immersion, so this is equal to rho VG because total immersion, and this is rho VG, not different. This is the density of the block. This is density of the float. Okay, and then we find acceleration, and we don't know the M, we don't know the V, but we know M. M equal to rho V. Okay, this is rho V. So the V cancelled out. Okay, we got 8. We have everything inside. We put A. So this is 1200. This is 800. This is 9.8. This is rho is 800. Okay, and we found it's 4.9 meter per second per second. The equation of continuity. Ideal flows in motion. Here are 4 assumptions that we make about our ideal flow. What is ideal fluid? 1. Steady flow. In steady flow, the velocity of the moving fluid at any fixed point does not change with time, either in magnitude or in direction. 2. Incompressible flow. That is, its density is a constant. uniform value. 3. Non-viscous flow. An object moving through a non-viscous flow would experience no viscous drag force, that is, no resistant force due to viscosity. 4. Irrotational flow. In irrotational flow, the test body will not rotate about an axis through its own center of mass. So many secrets like this: smoking, cigarettes, okay, the car, intestine, and so on. A fluid element P traces out a streamline as it moves. This is a streamline. This is a flow elements. Okay. The velocity of the elements is tangent to the streamline at any point. A streamline is the path traced out by a tiny fluid element, which we may call a fluid particle. As the fluid particle moves, its velocity may change both in magnitude and in direction. However, its velocity vector at any point is always tangent to the streamline at that point. The streamlines never cross, because if they did, a fluid particle arrived at the intersection would have two velocities simultaneously, an impossibility. A tube of flow is the tube whose boundary is made up of straight lines. Assuming that the fluid is incompressible and cannot be created or destroyed, thus, in the same time interval, the volume of flow which comes in the tube must be equal to the volume of flow which goes out of the tube. Three conditions. Okay, three conditions. Okay. This is the fluid is incompressible. Second, it's not created or destroyed. The equation of continuity. Look at this tube, a streamline tube. Okay, we see this one, the value tube is going in, and at the same value, the green one is going out. We see, okay, the fluid flows from the left to the right at a standing rate through the tube segment of length L. Okay, what is this? This volume is the area AI times VI. XI is VI over T. Okay, and this out E are the same. So we have AI VI delta T equal to delta V in equal to A 2 V2 delta T. We cancel delta T, we find out AV is a constant. This is called equation of continuity. Sample. The cross-section area A0 of the aorta, the major blood vessel emerging from the heart of a normal resting person, is 3 centimeters square, and the speed V0 of the blood is 30 centimeters per second. A typical capillary diameter 6 millimeter has a cross-section area A equal to 3 times 10 to the minus 7 centimeters square, and a flow speed V of 0.05 centimeters per square. How many capillaries does such a person have? We know the continuity flow. Okay, so A0 V0 equal to NAV. This is a capillary. Okay, this is aorta. Okay, and we put the number inside, we get an N. Very simple. 6 billion, very huge in our body. Figure shows how the stream of water emerging from the faucet next down as a fall. The cross-section area A0 is 1.0 centimeter square, and A is 0.35 centimeter square. The two levels are separated by vertical distance h, 45 millimeter. At what rate does the water flow from the tap? You want to find the AV actually, okay? Now, let's see this one. We see AOVO equal to AV. This is a continuity of fluid, okay? And what the relationship between VO and the V? Because it is a free fall acceleration. So we have V squared equal to V0 plus 2GH, okay? So we get this one, and we put this one. V is AV0 over A equal to V0 plus AV. In this case, okay, in this case, we know A0, we know A, we know H, we can find the V0, okay? Let's get the V0, okay? Once we get V0, we can get this one. The A0 V0, okay? 1 second, you have 34 cubic centimeter.
This water-filled cylinder is attached to a motor so that we can spin it at a high speed. When the cylinder is spinning, what will happen to the surface of the water? We'll begin by spinning the cylinder slowly, then increasing the speed. At first, the water surface stays more or less horizontal. As the speed increases, the water begins to climb up the wall.
This curve is parabolic.
When the speed is great enough, the parabolic shape of the water surface becomes clear.
Bernoulli's equation. Bernoulli's equation. For an ideal flow, no viscous force, P1 at one point, pressure at P1 plus half rho V1, the speed of the fluid, square, plus rho g y1, the location of V1, equal to P2 plus half rho V2 square plus rho g y2. In other words, P plus half rho V square plus rho g y is constant. I'm going to prove it later. If the speed of a fluid element increases as it travels along a horizontal streamline, horizontal streamline means y1 equal to y2, and the velocity speed, the pressure of the fluid must decrease. This increase, this decrease, okay? And conversely, Bernoulli's equation is strictly valid only to the extent that the flow is ideal. What is ideal? We mentioned 4 points. If the viscous forces are present, thermal energy will be involved. We take no account of this in the derivative of that follows. In the following deduction, we don't consider the viscous force, okay? Now, we see this tube, the fluid flow from this side to swim. At the moment, say, we have a pressure P1, there's pressure P2, and there's a liquid press in, and this is out. Now let's see the situation, okay? This is where you want to find the proof, okay? How do we find it? You see, we see all this one, it goes up, it changes the velocity, it changes the potential energy of gravitational. What we do, we use delta K equal to W. The work done by these forces, P1, P2, gravitational force, equal to the kinetic energy change. What is the kinetic energy change? What is it? Half delta M V2 squared minus half delta M V1 squared. This is the mass M delta M. In, it is a mass out, okay? Inside the same, all right? This is constant. So we take the delta M out, and the delta M equal to rho delta V. That's the volume of this one. What's the W? We have two forces involved. One is the gravitational force, one is the pressure at the water. Let's see the gravitational force that equal to mgh minus. This is a gh, this is a potential energy of gravitational, minus is the work done by the gravitational force. This by definition, right? Yeah. With the pressure has a two. This is press in, this is press out. Okay. This is delta M, is mu delta V. And W by the pressure is a 2. Okay. F2 x2 plus F1 x delta x1. Okay. This is positive, this is negative because F's go this way. So we get a minus P2A2 delta x2 plus P1A1 F1 delta x1. Now, W delta K, we put them together. Okay? Put them together. Half rho delta V G Y2YC plus minus P2 plus V1 delta V equals delta K, half rho delta V plus C. And we cancel the delta V and we find P1 plus half rho V1 squared plus rho Y11 equal to P2 plus half rho V2 squared plus rho G. That's the equation. We prove it.
As water flows through a tube, its pressure drops. If the tube has a constant diameter, the pressure drop increases regularly along the length of the tube. We'll use this device to show what happens when the diameter of the tube is not constant. Water flows through this horizontal glass tube, which has a large diameter at the beginning and end, but a constriction in the middle. The pressure in each of the sections is indicated by the water level in the vertical tubes. The two outer vertical tubes show the pressure drop that occurs along the horizontal tube. The center tube is covered. If the pressure drop was constant, we would expect this tube's level to be here. Will that be the actual height, or will it be higher or lower? The water level in the center tube is lower than expected, showing the lowered pressure in the constriction.
This glass pitot tube can be used to measure the velocity of an airstream flowing past. The pitot tube is a water manometer with two openings, one facing into the airstream and the other perpendicular to it. When air flows past the pitot tube, there is a difference in air pressure at the two openings, which causes a difference in water levels within the manometer. The difference in water levels depends on the speed of the air. When we increase the speed, the difference in water levels increases.
This device is known as a Flettner rotor. The rotor is a styrofoam cylinder powered by a small electric motor and mounted on a rolling car. When switched on, the rotor spins clockwise as seen from above. If we direct a stream of air from a fan at the rotor, the car moves perpendicular to the airflow. Reversing the direction of spin reverses the motion of the car. This animation shows how the moving air stream is deflected as it flows around the rotor, causing a reaction force which propels the car to the side.
A pitcher can make a baseball curve by applying the proper spin to the ball as it leaves her hand. We're going to increase the effect by using a light styrofoam ball and a throwing tube, which will put a fast spin on the ball. If the ball is thrown overhand as shown, so that it comes out spinning clockwise as seen by the camera, the ball curves upward. If the direction of spin is changed by throwing the ball side-armed, the ball curves away from the direction of the throw. This animation shows how the stream of air moving past the ball is deflected by the spinning of the ball.
If a jet of air from a blower is directed straight up, a styrofoam ball will float inside the jet. It stays there even if we tip the jet sideways, as long as we don't tip the jet too much.
If we blow air through the hole in the center of this disc, light objects such as this streamer are blown away from the disc. If we put a second disc up to the first with the air blowing, what will happen? The second disc is pushed up against the first because the air moving between the disc is at a lower pressure than the air beneath the lower disc. Even if we attach a weight to the lower disc, it still hangs beneath the upper disc.
These two parallel plates swing freely on strings. If we blow air into the space between the plates swing together.
Sample. Ethanol density rho 791 kilogram per cubic meter flows smoothly through a horizontal pipe that tapers in cross-section area from A1 1.20 times 10 to the minus 3 square meter to A2 equal to half A1. The pressure difference delta P between the wide and the narrow section of the pipe is 4,120 Pascal. What is the volume flow rate R of the ethanol? What we want, we find this one. A1V1 or A2V2, okay? Actually, we want to find, because we know the A, so we want the V1 or the V2, okay? What we do, we use this Bernoulli equation, okay, at two terminal, okay, two terminal. And then you see the horizontal, like they are horizontal, so H1 equal to H2, they cancel out, okay? So delta P equal to half P1 minus P2 equal to half rho V2 squared minus half rho V2, okay? And we know it's given 4,120 Pascal, okay? And also we have A1 V1 equal to A2 V2. So these two equations, basically we can find the V, okay? Okay, we'll put it inside, we find the V. Once we find the V, we can get the rho. So this is V1, which is the AO, we get the VO. Sample. In the Old West, a demonstrator fires a bullet into an open water tank because water is so crucial for the desert, okay, at West, okay. Create a hole, okay, a distance h below the water surface. What is the speed v of the water emerging from the hole? Now, this is we use the Bernoulli equation. We see the AV equal to AV0, okay? And then we know the V0, okay, should be much, much smaller than V. And then we use the Bernoulli equation. Suppose this is y equal to 0. So this surface y equal to h. So we had a P0 half the rho V0 plus h, this is 0, okay? This is a P0 atmosphere. So they cancel out. And we get V about square root 2gh like the free fall. Next chapter. Chapter 14, oscillations. welcome you make a comment and give suggestions so that this program can be more helpful. Acknowledgement. This video clip is a part of my lectures on college physics during 1990 to 2021, based on the adapted textbook, Principles of Physics by Holliday, Resnick, and Walker, published by Wiley. The demo videos were bought from a company in USA by my university for teaching. They help a lot. I'm sorry for not remembering its name to show my appreciation. It seems that they came from the University of California, Santa Barbara, where I got my PhD in physics. Thanks God.